So this section is on rates of change in the sciences, and we'll do a couple science-related things, but we're going to start off with a little bit of physics, which is definitely science. Then we're going to talk a little bit about, motion, and we'll talk about some economics and some stuff like that. So hopefully you see the application of these calculus ideas that we've been doing. So far we've talked about the derivative of position is velocity, okay? And the derivative of velocity is acceleration, okay? So that means the second derivative of position is acceleration. And we talked about this relationship. We're really good at going this direction. So if I've got a position function, and we normally call that s of t, so that's the position with respect to time. So the position function is s of t. If I find ds dt, if I find the derivative of s with respect to t, well, that gives me the velocity. So we'll represent that in function notation as v of t. Second derivative of position, or we call that d squared s dt squared. Okay, second derivative of position with respect to time would be the first derivative of velocity with respect to time. So the second derivative of position is the same as the first derivative of velocity, and that's going to be the acceleration. And then we talked about this one right here. What's the third derivative of position? Okay, that's called the jerk. And I suppose we could call that j of t or something like that. I don't think that has a special name. I think things fall apart after that. Okay? So a couple of things that we want to make sure that we're clear on so that we can do problems like this is the difference between speed and velocity. And if you've had a physics class, they make a huge difference between those things. So speed only measures how fast you're going. Okay? So we say it measures the magnitude. Okay? So magnitude. And velocity measures not only how fast you're going, but it's usually got a sign associated with it or some sort of directional indicator. Okay? So it measures magnitude and direction. Very good, like a vector. Yep. Okay. So we're going to use this little trip right here, and we're just going to kind of investigate these ideas. I live in South Jordan, and my parents live in Idaho, Blackfoot, Idaho. I grew up in Blackfoot, and it's almost 200 miles exactly from my door to their door. Okay? So I'll be honest with you, I made this trip up, but I suppose it could represent something I actually did. I took a trip something close to this. Hopefully not all the stuff that we're going to talk about actually happened on here, because that may or may not be good. Okay? So what this is this is a position function right here. And you can tell it's a position function, not a distance function like the one that you graphed in Project 1, because you'll notice here I've got some positive positions and I've got some negative positions. Okay, we couldn't have negative distances on here. Okay, so South Jordan is represented as kind of the reference point. That's my house. We're going to call that 0. Blackfoot is north of here, so we're going to think of north as in the positive direction, and it's 200 miles away. So here's Blackfoot, represented by that 200-mile position right here. Okay, and then we're going to talk about this in just a second as we run through this kind of story of my little trip. Okay, and I'm not such a complete nerd that I do this all the time, but I just made this up for illustrative purposes. Okay, so a couple questions right here to kind of figure out what's going on here. It says, what is the average velocity, average rate of change of position with respect to time from 0 to 2? So time 0 to time 2. And this is in hours here, and this is in miles along the vertical axis here. So what we do in order to figure that out is we'd figure out, well, what was my change in position divided by my change in time? So at 2 hours, I'm about right here, okay? In the neighborhood of 160 miles away from home, okay? My change in position, I started out at 0 and I ended up at 160. So that's going to be 160, and the units there would be miles. And how many hours did I take there? Change in time was 2. So we're literally calculating a slope, just like we learned how to do in chapter 2. So this would be 2 hours. So my average rate of change was 80 miles per hour. Okay? Okay. What is my speed at t equals 12? So let's take a look at this right here. We'll go over to 12. And speed on this graph would be indicated by the slope of the position curve, right? So we'd have to find an average rate of change. It looks like it's pretty straight here. So let's just go from here over to there. So this would be a change in 50 miles, and this would be 1 hour. So what is my speed there? What's my average rate of change there? Okay, so let's make sure we're clear on this. So this would be 50 miles per hour. If we were just talking about how fast I was going, we found the slope on the position curve. We found that it was 50, or at least that looks like it's a pretty good approximation for what the slope is right there. Okay, and we found that that rate was 50 miles in the vertical, 1 hour in the horizontal, so 50 miles per hour. Okay, if I say what's my speed, it doesn't matter whether I'm going north or south. It's just 50 miles per hour. We're asking what does the speedometer read approximately at that time, and it would read 50 miles per hour. Okay, if I change that question slightly and I said what is my velocity at t equals 12, what would the answer be then? Okay, then it would be negative 50 because I was going south. South in this frame of reference is in the negative direction. So my rise would be negative 50. My run would be 1 hour. So negative 50 miles over 1 hour. So that's going to be negative 50 miles per hour. Okay? Then let's look at this and let's think about this for just a second. This is a position function. And the next question is, when was I not moving? When was I not moving? And how can you tell? Okay, when it flattens out, right? Okay, now, if you looked at your project, I went through and graded those. They were pretty well done. I went through and I circled parts on both of those graphs, and then I wrote some corresponding numbers. If you look at where your position graph or your distance graph just sits there for a little bit, look at your velocity graph. Okay, think about that trip that you made. Yeah, what was happening to your velocity? What was happening to your speed? Most of you took a trip on Bangalore and you were stopped at a red light. So you can look at the velocity graph and say, hey, we're not going anywhere, so my distance isn't going to change. Or looking at it this way in terms of rates of change, what's the rate of change here? 0. Okay, I've got a constant. My slope here, the derivative, is 0. So that means I'm not moving at all. My rate of change of position is 0. So that means I'm staying still from here to here. So about from 3 to 7 hours, okay? Whatever my stopwatch was or whatever. So from 3 to 7 hours, then again from 8 to 9, then again from 10 to 11, and then again from 13 to 14. So let's write those down. When was I not moving? So from 3 to 7, hour 3 to hour 7, okay? From hour 8 to hour 9, again from 10 to 11, from 13 to 14, and then the last time was about from 15.5 to hour 16. Okay, next question. When was I going north? Okay, so from about 0 to 3, right? I was going north from 0 to 3. And how can you tell I was going north? Positive slope or slope on a position function represents my velocity, so I had a positive velocity. So I had a positive velocity from 0 to 3. When did I have a positive velocity again? We got positive slope here. I got a little positive slope right here. That would be from about 7.5 to 8. And then again from about 14.75 to 15.5, somewhere in that neighborhood. Does that look okay? And the reason for that is I have a positive slope on the position curve. So that means I've got a positive velocity. In this frame of reference, north is positive. Okay? So if I've got a positive velocity, I'm heading north. And then, of course, I'd be going south from, looks like 7 to 7.5. And then again, I'm heading south. Gosh, looks like 9 to 10. And then 11 to about 13. Okay. So, what was the total distance traveled? Yeah. Oh, okay. Yep. 14 to 14.75. Thanks. So we got these times right here, and then I was heading south again right here. Okay. So let's look at this graph, and before we answer how much distance I traveled, let's see if we can figure out exactly what happened on this. Okay. So headed off from my house, headed north, pretty fast. Got there in 3 hours. 200 miles in 3 hours is pretty fast. Okay. A little less than 70 miles per hour on average. Okay, look at how steep this part of the graph is, and then look how steep this part of the graph is. Okay, this represents me going, we figured out about 80 miles per hour. What happened at about 2.5 hours? What happens right here? Okay, got off the freeway, or at the very least, I started to slow down. Because this slope is a lot different than that slope right there. That velocity is much different than that velocity right there. They're both positive. Okay, so I'm still heading north, but I'm slowing down. Okay, then my slope is 0. So I stopped. For about 4 hours, hung out with my parents for a while. Okay, then what happened? Yeah, maybe I went to the grocery store, but my gosh, the grocery store would have to be about 25 miles away. Okay, Blackfoot's not that podunk. Okay. Headed back toward Utah. If I was still heading south, okay, unless I hopped on a road that was heading north, I wouldn't head back there. Probably forgot something. Got 25 miles away, got to about Pocatello, Idaho, forgot something, and then turned around. And I want you to take note of something. Let me blow this up here. Okay, and some of you pointed this out in your project. Take a good look at this. Did I come to a point and did I immediately change direction, or did it kind of level off for just a second? Okay, even if I get off an off-ramp and make a U and turn around and get back on the freeway going the other direction, aren't I going to have to stop just for an instant? Yep. At least my north-south motion is going to stop just for an instant, because I'm going to be heading south, and then I'm going to turn around. And in order to turn around, as some of you pointed out, I can't change direction instantly. I can't change speeds and velocities instantly unless some of you had the happy thought of the only way for that to happen is to get in an accident. Okay, you got to hit a brick wall to stop instantly. Okay, so I stopped for just an instant, and then I went back, got whatever I forgot. Okay, I'll use see, that's why I'm a mathematician. Okay, get whatever I forgot, and then I hung around for an hour, and then headed home. Okay, now tell me something about this right here. Okay, let me slide that over so you can see. How fast was I going there? Okay, this is a change of how much distance? Okay, 100 miles in how long? 1 hour. What happened right here? Got pulled over. Hung around, talked about what I forgot it in Blackfoot. That's the way they talk up there, by the way. Okay, so got a ticket. Okay, now, no, of course not. Okay. So this was pretty reasonable speeds here. This is freeway speeds here, even slower than freeway speeds. This is way too fast. Got pulled over. Tell me something about this velocity versus this velocity right here. And in fact, all the way home. What's that? Yeah, I got a little gun shy. Got pulled over, got a ticket, and then I thought, you know what? I'm going to play it safe. Okay, so in this 1 hour, I covered 100 miles. In this 2 hours, I covered 100 miles. So my rate of change was half of what it was before. Okay, make sense? Okay, where did I go here? If 0 is South Jordan, where did I go here? Itinerus is north of South Jordan. Would have had to go to Provo. Okay, if you look at the scale here, I went about 45 miles away. Provo's about 45 miles away, so I went to Provo here. Okay, so I went to Provo, picked something up, turned around, headed back. Really wasn't there very long, was I? How can you tell that I wasn't there very long? because it immediately comes back. If I hung around there for even 5 or 10 minutes, it would have flattened off, and then I would have headed back home. Okay? What's that? North is that way. Yep. Okay. All right. So now let's talk about displacement. Displacement is what we call the net change in position. So how much did your position change? Okay, and it can be positive or negative. So my displacement, and we'll come back here and we'll answer this total distance question in just a second. What was my displacement from 0 when I started my stopwatch at the beginning of the trip to 2? What was my displacement here? Okay, about 160, 150 miles. That was my displacement. What was my displacement from 0 to t equals 4? 200, because I was 200 miles away from my reference point from my home. Okay, what about at 13, from 0 to 13? 0, okay? My displacement was 0, but does that mean I didn't go anywhere in between 0 and 13? It doesn't, okay? And what about 0 and 14.5? Negative, I'd say about negative 30-ish or somewhere around there. Definitely negative, okay? Whatever it is, you know, precisely what it is doesn't really matter, okay? Now let's talk about the total distance traveled. Even though from 0 to 13 my displacement was 0, I traveled 200 miles up and I traveled 200 miles back. Doesn't really matter that I stopped on the side of the road for an hour. Okay, I still traveled 200 miles back. So there's up and back, so there's 200 miles up, 200 miles back. What about this right here? See why that's so aggravating when you forget something and have to turn around? Okay, that's 25 miles heading home, turn around 25 miles. That's 50 miles right there. Okay, that one little mistake cost me 50 miles, probably an hour. Okay, more because I sat around and talked. Okay, so I've got 200 miles there, 25, 25, 200. I'm up at 450 now. Okay, and roughly what happened here? About 45 there and 45 back. So we'd be looking at about 540 miles represented here. Okay, any questions? Okay, so let's go from a problem where we can look at this and think in terms of, I mean, you made graphs kind of like this, where we can kind of think of, okay, realistically what would happen in the real world, and we can come up with a story to fit that. Okay, now let's take kind of more of a physics approach to this, and let's say that we've got a stone that's thrown straight up with a launch velocity of 64 feet per second from a bridge, and that bridge is 96 feet off the water. Okay, then the stone's height, or we could read that as the stone's position above the water, can be given by this function right here. And it says, find the velocity and the acceleration functions, and then add the acceleration to the graph below. So here's its position function, here's the velocity function, and it says we want to find the velocity and the acceleration. Okay, so the velocity would be the derivative, right? So that's going to be v of t, so that's going to be negative 32t plus 64. Good there? Does it make sense as to why this graph is shaped the way it is? If this is the velocity graph, that means it crosses at 64, about right there, and then notice it's linear, and it's got a negative slope, so it's going down 32 feet per second. Okay? And then let's find the acceleration function. So the acceleration function would be negative 32. So if this gives the answer for position in feet, this gives the answer for velocity in feet per second. And this would give the acceleration in feet per second squared. Okay? So if I were to graph the acceleration function would have to be about right there at negative 32. It's always negative 32 feet per second squared. Up is positive, gravity's pulling it down at negative 32 feet per second squared. Okay? Is the stone going up or down at 4 seconds? Answer's down. Okay, now here's the real question. The real question is, how do you know? Okay, there are a couple ways to tell. Okay, if you look at this, this is when it was going up, its position was increasing, and now its position is decreasing. We could look at the graph and we could say, you know, at 4 seconds, I can tell that the slope is negative, so it's got to be going down. Or we could look at it and say, well, whether you're going up or down, the direction that you're traveling is indicated by the velocity. Velocity will tell you how fast you're going and in which direction you're headed. So if you look at the velocity right here, at 4 seconds, let's go over here, it's about right there, the velocity is negative. You got to be going down. Okay? So I'm going to write velocity is negative. If you see that from the slope of the curve there, that would be fine also. Use calculus to find the highest point reached by the stone. Well, we can see where the highest point is, and we could probably guess the time at which it reaches its highest point. But let's think about what happens. When you throw something up in the air, it goes up, slows down, and then it changes direction. Like we talked about just a second ago, when it changes direction, what happens to its velocity? It's 0, okay? So the slope of that position curve would be 0, or the velocity would be 0. So all we're going to do here is we're just going to find where does the velocity equal 0. So we'll take negative 32t minus 64, excuse me, plus 64, set that equal to 0. So negative 32t equals negative 64. I get t equals 2 seconds. That's when it reaches its highest point. That's the time at which it reaches its maximum point and starts falling back down. How do we find its position, its highest position then? Plug it into the original one. So we're going to find s of 2, and that's going to be negative 16 times, I'll just do this, we've got 4, then plus 64 times 2 plus 96. So this is going to be, let's see, it's going to end up being 96 plus 64. So it's going to end up being 160. 160, did I do that right? Okay. 160 what? Feet. Okay. Maximum height is 160 feet. The way we found that was not by finding the vertex of the parabola, but thinking about, well, when would the velocity be 0? Because it went up, stopped for just an instant, and then headed back down. So using calculus, okay, not that negative b over 2a stuff that you learned in pre-calculus, okay, we can find that using setting the velocity equal to 0, okay? So with what speed does the stone strike the river? How would you find that? What's that? We could somehow use acceleration if we wanted to. I think there's a little bit easier way to do it. What would you need to know first? Yeah, when did it hit the river? Now you can tell based on this position function that it hits the river at about 5 point something seconds, a little bit more than 5 seconds. How would we find that? Yeah, set the position function equal to 0. So let's go ahead and do that. So I'm going to do 0 equals negative 16t squared plus 64t plus 96. Let's go ahead and solve this. I'm going to divide everything by negative 16, so that's going to give me a little bit easier quadratic. So that's going to give me t squared minus 4t and then plus 5. Correct me if I've made a little mistake there. Divide both sides by negative 16. It gets rid of the coefficient in front. Oh, it would be negative 5. You're right. Very good. 6. Take that. Got it? Divide all these by 16. We get a 1 here. We get a negative 4 here. And we get a negative 6 there. Okay. This is a quadratic. Could we solve it by factoring? Because that would be the easiest way to do it. Nope. Okay. So let's solve it using the quadratic formula. So that's going to be t equals, that's going to be 4 plus or minus b squared. So that's going to be 16 minus 4 times a times c. So that's a 1 and a negative 6 all over 2. Usually best not to skip this part. That's going to be 16. It's going to be a plus 24. So we'll have 4 plus or minus. Do I need the minus one? I don't. Not on this one, because we know we're trying to find that positive answer there. Okay? So this is going to be radical 40 all over 2. And if you throw that into the calculator, did I do that right? Got a radical 40, right? Okay. Throw that in the calculator, what do we get? Yeah, let's hope it's larger than 5. Anybody got a calculator? Throw that in there. Okay, so 5.16. What are the units on that? Seconds. 5.16 seconds. Now, hopefully you've stored more than just 5.16, just 2 decimal places. It may give us a slight inaccuracy. But it says, with what speed does it hit the river? Well, we know it hits the river 5.16 seconds after we threw that up in the air. So if you want to know how fast it was going, which equation do we use? The velocity. So let's find v of 5.16. So that'd be negative 32 times 5.16. And I'm trusting that somebody's doing the arithmetic here for us. So what is that? Okay, so 101.19. And what would the units be? Okay, that's going to be feet per second. Okay, now that's the speed. If you plug this in and got the actual velocity, correct me if I'm wrong, but that would be negative. So if we said the velocity, it would be negative. If we said the speed, we just take the absolute value of velocity and we get 101. Okay, any questions there? Okay, so this is the velocity. Take the absolute value, and this would be the speed, 101.19 feet per second. Okay, so we got that right there, 101.19. Okay, when is the rock slowing down and when is it speeding up? I mean, everybody's throwing something up in the air. When is it slowing down? Okay, so from 0 to 2 seconds, it's slowing down, and then it's speeding up all the way until it hits the water, right? So from 0 until 5.16. Slowing down, 0 to 2, speeding up, 2 to 5.16. Of course, those are in seconds. So could we figure out a rule that will tell us when it's speeding up and when it's slowing down? Slowing down here, because gravity's pulling it down. Speeding up here, because it's heading down and gravity's pulling it down. Any ideas? Maddie? Yep, it does. That's exactly what it has to do with. So Maddie says, does it have something to do with when the velocity function is positive and when it's negative? Yes, it does. But it depends on when the velocity is positive and negative, and one other thing. When the acceleration is positive and negative. Okay? So let's think about why this was slowing down. The velocity was positive. We threw it upward. Okay? Positive velocity going up. Gravity's pulling it down. Those two things are working in opposite directions. Okay? Then once it starts to go down, having a negative velocity, these two have the same sign. Acceleration is negative and velocity is negative. Okay? So it speeds up. Okay? So could we come up with a rule? Okay? So it's going to slow down when what? When what's approaching 0? Okay, but what would make it slow down? What would make the velocity approach 0? You're right, but what would make that happen? When velocity and acceleration, what is it? Are opposite signs. So what would make it speed up? Okay, when velocity and acceleration are same sign. Okay, so what if acceleration was positive and velocity was positive? It would speed up. It would continue going up. Okay, if velocity is negative and acceleration is negative, it's going to speed up in the negative direction. But whenever they're playing against each other, okay, it's going to slow it down until it eventually turns it around and heads in another direction, possibly. Okay? All right. Any questions there? Okay, good. Let's see. I think we can finish this one right here. So we've gone from a situation where we could come up with a story and everybody's driven places and we can kind of understand what's going on there as far as position and velocity, okay, to a little bit more science-based, a physics example where we're throwing a rock up in the air, where we still have some physical representation for that and we understand the situation there. And now we've got an equation for it, to something called, this is called rectilinear motion. Okay, this is motion along the line. And the classic way of describing this is saying we've got a particle that moves along a horizontal line and here's its position function. You'll notice the position function is a little bit more difficult than the last one. Okay? And how often do we sit and stare at a particle moving along a line? Okay? Doesn't happen very often. Okay, so this is getting a little bit more abstract, but let's run through the questions here. So we've got our position function, and it says t is in seconds, s is in meters, and we're only interested in this, or this particular model for this motion only works from 0 to 5 seconds. Okay? So we're only tracking this particle's position for a short amount of time. Okay? It says, what is the initial position, and what is the final position? In other words, where is it to start out with, and where is it when we're all done with this? Okay? So let's do S of 0. If you plug in a 0, you get 0. So in other words, 0 meters. Haven't moved anywhere. We're right at the origin in this particular case, right at our reference point of 0. And S of 5, if you plug in a 5, let's see, that's going to be 125. That's going to be minus 150, isn't it? And then plus 45. Did I do that right? So what do I end up with? It's 20, isn't it? Positive 20. So we end up on the positive side of whatever our reference point, 20 meters on the positive side. Find the velocity at any time t. What do? What derivative? Velocity? Just the first derivative. So we're going to find v of t. We'll find the derivative here. That's going to be 3t squared minus 12t plus 9. There's our velocity function. Find the velocity at 2 seconds. So find what v of 2 is. So let's plug in a 2. That's going to be 12. Minus 24 plus 9. So what do we end up with? Negative 3. What would the units be? Okay, I'm going to put that here. I forgot to do that. Meters per second here, and that would be meters per second here. Is the particle moving to the right or to the left? Okay, particle's moving to the left, and how do you know? Because it's negative. Okay. And in this frame of reference, we're assuming right is positive, left is negative. Okay? V of 4. So we'd plug in a 4. Let's see. So that's going to require a little bit of work here. Grab your calculator and make sure we get this right. So that's going to be 48. Oh, well, that's not too bad, is it? 48 here, minus 48 here, plus 9. So the answer is 9 meters per second. Right or left? Right. And the reason is important because the velocity is positive. Okay? Next question. When is the particle at rest? we have a position function and we have a velocity function. Which of those two is going to tell us when it's stopped? Velocity. We want to know when the velocity is equal to 0. So let's set this equal to 0. Get rid of that leading coefficient of 3. So here's what we're solving. We're solving 0 equals t squared minus, let's see, 4t plus 3. Is that right? Which I can then factor, and I end up with, let's see, t minus 1 and t minus 3. So when is the particle at rest? At t equals 1 and at t equals 3. And again, since those are times, those are seconds. Okay? So at 1 second, it's stopped, and at 3 seconds, it's stopped. And then it says, what is the particle's position when it's stopped? So it's stopped at 1 second, so we want to know what is s of 1. So we plug in a 1. 4, is that right? What are the units? Meters. And it stopped again at 3, so let's figure out what s of 3 is. So if I plug a 3 in here, I've got 27 minus 54 plus 27 ends up being 0. Okay. Okay, so let's take that information, and I've got a horizontal line right here with a reference point. So this is 0, okay, and that's the positive direction, and that's the negative direction. Okay, same old x-axis. And let's draw a diagram of what happened here. Okay, so the way we do these, don't write anything yet, is let's mark down the information that we have. Okay. At 0 seconds, its position is 0, so it's right here. And I'm going to write t equals 0. It's right there. Okay, the next piece of information that we have, notice that I've tried to color coordinate here. The position stuff is in black. The next piece of information that I have is at 1 second, it's at 4 meters. Okay, so 1, 2, 3, 4. Okay, I'm going to do this. I'm going to put a point right there, and I'm going to say that's at t equals 1. The next bit of information I have, the next time I have, is 3 seconds, it's back at 0. So I'm going to put right here. So this would be t equals 3. And then when I'm done, at 5 seconds, it's 20. Its position is positive 20. So that would be way over here at t equals 5. So it did this. So that's why we call this a diagram. Okay, this is a diagram of the rectilinear motion. Okay, it started off at 0. It got to 1, turned around, got back to here, turned around, and then headed there. Now, the reason we do a diagram like that is it would look pretty funny if we did this, went to here, back to here, and like that. You really wouldn't be able to see it. So we kind of stretch this out just a little bit so you can see what the motion was. Okay? Any questions there? Okay. When is the particle moving to the right? And when is the particle moving to the left? So we can tell just based off our position diagram that it started at 0, it headed right for 1 second, then it headed left for 1 second, 2 seconds, and then it headed to the right again. So when was the particle moving to the right? 0 to 1, and then again from 3 to 5. And it was moving to the left from 1 to 3 seconds. Okay. So this says graph the position curve, and here's what we're going to do. We're going to graph this on a TS axis. Oops, let me change colors again so we're keeping these color coordinated. So this is a TS axis. It starts off at 0. At 1 second, it's 4, so I'm going to make sure I've got enough space for this. So we'd be about right here. At 3 seconds, it's back at 0. And then at 5 seconds, it's at 20. So 5 seconds would be about that high. That's what it would look like. You can see some similarities between the diagram that we drew of how it would move back and forth along the line and what the position function looks like. And I'm going to change colors here because the next thing it says is graph the velocity curve. Graph the velocity curve. Here was the velocity function, this one right here. And we know some important things. We know that the velocity is 0 at 1 and at 3. So let's come down here. And at 1 and at 3, the velocity is 0. This is our time axis, and this is our velocity axis. This would be meters per second. And it's a parabola, isn't it? So it looks something like this. You'll notice that I didn't put hatch marks on the y-axis here. So I guess we only need to go to 5 and here. Positive velocity, moving to the right. What happens in between 1 and 3 seconds? Negative velocity, moving to the left. And what happens once we get between 3 and 5 seconds? Moving to the right again. Okay? Let's come back up here. Then it says, find the total distance traveled by the particle. Well, let's see. It was 4 this way, 4 back, and then where did it end up? At 20. So 4 here, and 20. So altogether, that's going to be 28. 28 meters. Okay, find the acceleration. Acceleration at any time t, we're going to find a of t. So we're going to find the first derivative of velocity or the second derivative of position. So that's going to be 6t minus 12. And it says, find the acceleration at 1 second. So we want to find a of 1. That's going to be negative 6 meters per second squared. And it says, find it at 4 seconds. So let's find a of 4. That's going to be, let's see, that's going to be 12 meters per second squared. And then we're going to come down here and we're going to graph the acceleration curve. So the acceleration curve is 6t minus 12. So 6t minus 12. Where does that cross? What's the t-intercept? Where does that hit 0? No, on the t-axis or the x-axis. It'd be at 2, right? When is the acceleration 0? At 2. So it looks something like that. Okay, now what we've got here is a diagram very similar to this one right here, except for it's separated. Here's position, here's velocity, here's acceleration. Okay, and what is the last question on that list? When is it speeding up, and when is it slowing down? So let's stop and think about that for just a second. Speed up, slow down. We figured out on the last question a way that we could tell. It's got to do with velocity and acceleration. If it's speeding up, velocity and acceleration have same sign. And if it's slowing down, they have opposite signs. So let's look at this, and then we'll come back up and look at the diagram again in just a second. Let's look at this and figure out when would this be speeding up and when would it be slowing down. Let's take a look at the 1 second interval, this first second right here. Velocity is positive, acceleration is negative. So from 0 to 1, it's going to be slowing down. Let's check and see what happens here. From 1 to 2, velocity is negative, acceleration is still negative. So from 1 second to 2 seconds, it's going to be speeding up. From 2 to 3, negative velocity, positive acceleration. So from 2 to 3, it's going to be slowing down. And then what happens from 3 seconds on? Positive velocity, positive acceleration. So it's going to be speeding up. Okay, let's come back up here and let's take a look at this. Okay, it was going fast and it started to slow down. It's got to slow down in order to make that smooth transition from going to the right, like we talked about, to going to the left. So it's going to be slowing down. Once it makes that turn, it's going to be speeding up for just a little bit. Then it's got to slow down to make that turn again. So somewhere in between here, maybe about right there, not quite sure what the position is, but somewhere around t equals 2, it's got to start slowing down to make that turn. Okay, but what happens once it slows down to make that turn? Speeds up and speeds up and speeds up. That's why in these 2 seconds, okay, because the acceleration was going in the positive direction and the velocity was going in this positive direction, that's why it was able to cover so much territory. Okay? All right, let me add one more thing to this. Okay, acceleration is negative right here. It's pulling it this direction. So it's going to slow down because it's being pulled to the left. And then once it makes that turn, stops for an instant and turns around and heads to the left, it's going to speed up. But partway through that turn right there, the acceleration changed. It went from being negative to being positive. So let's come up here and take a look at what happens there. If it's being pulled now to the right, it's going to slow it down. But again, once it stops for an instant and makes that turn and heads in the same direction of the acceleration, it's going to speed up and speed up and speed up and speed up. Okay? So Juan has stuck around after school and asked questions about, what would the normal line do and the tangent and all that sort of stuff. There are lots of applications for these types of things in physics, okay, in astronomy. It can help explain why if you've got some, stray asteroid, why it has a path that does something like this. There might be some planet right here or some moon right here that pulls it in this direction, makes it curve over that way, okay? And then at some point right in between here, okay, in between these two gravitational pulls, okay, then it starts to head off in this direction. So for just a second, it might be heading in a straight line, but those accelerations, those forces due to gravity, kind of alter that course a little bit, okay? Kind of in a very simple, very oversimplified sense, what's going on here with this rectilinear motion, okay? All right. You've got enough time to get started on the assignment. We're going to cover some very pretty easy ideas tomorrow. This is only going to take us maybe 15 or 20 minutes. Come with questions on anything up until that point, and we may get started on 3.9 just to get you some flavor for that over the weekend. Okay? All right. Thank you very much.